Hi everybody and welcome to a AQA A-Level Design Technology revision video. Today we're going to be doing topic 3.1.4, forming, redistribution and addition processes. I've broken down everything on the specification in detail, covering everything that you need to know for this particular topic. So let's get started. We're going to be starting with paper and board forming processes because that's what it starts with on the specification. So the first process we're going to look at is kind of a fan favorite, die cutting. It's a process that cuts or creases shapes out of a flat piece of sheet material using a shaped die and press. The uses of this are typically for packaging or labels because we're using things like papers and boards. It's just a perfect application for creating a kind of packaging out of that. So what are the pros of die cutting? Well, it's quite fast. Given that it can be repeated very quickly, so it's suitable for mass manufacture, and it also creates consistent shapes because the die doesn't change shape once used. It's also a very low skill process because you don't really need any worker with particular skill to operate it, and you can also fully automate the process with a computer. The cons of it is that it is limited to flat material forms, so you have to use sheet materials with it. You can't use anything that's not a sheet material, which limits you to only 2D designs. And also the die can wear out over time. So particularly this is important for die cutting rather than die creasing. But that die wearing out over time means it will be less effective at cutting materials, which means we'll be likely having to replace it. And that links into the initial cost of the die, which is sort of an investment into creating a die cutting process or starting the die cutting process is creating that die. And that's obviously going to cost something. It's probably not going to be the most expensive tooling to get manufactured, but still definitely an initial upfront investment. So the process you need to describe in your exam is step 0 or step 1 is to design the template with the required cuts or creases. Then you'd mount the cutting die to the press, place the sheet material onto the cutting bed, align the material with the die, activate the press to cut or crease the material, remove and inspect the material, and trim any excess if needed. And the diagrams, by the way, there's going to be a diagram on most slides, and that is simply just to show you what it would look like. However, it's not entirely necessary to memorize or learn, or even for me to explain exactly what's going on in this diagram. It's just sort of to help you visualize what the process actually is and what it looks like. So next we're going to be looking at laser cutting. So laser cutting can best be described as a precise method that uses a focused laser beam to cut or engrave materials without physical contact. That's really important to mention, that it is without physical contact. What are the uses of laser cutting? Well, I'm sure many people who are watching, if there is many people watching, or I can confirm myself, have used laser cutting in prototype development for your NEA or portfolio. That's because it's quick, it's accurate, and it's precise. And you can do it with sort of materials where otherwise it'd be typically quite hard to make a prototype out of them. But you can make an accurate prototype out of, like, I don't know, foam board using a laser cutter. Another real world use for it though is like retail stands. So there's a lot of just like filler things in retail, like stands for shoes at a shoe shop that might have been line bent, but also cut out of a flat piece of acrylic using a laser cutter. So the pros of laser cutting, well, that it's very high precision because obviously we're being computer controlled. So that is assumed in the laser cutting process. For the A-level specification is that laser cutting is always computer controlled, CNC, which means computer numerical control. And also there's no tool wear, which is really good. So because there's no contact with the tool, there's no wear and tear from using a laser cutter, and that means that we can basically use it as much as we like, and maintenance is only going to be really when something on it breaks on the gantry. Another benefit of laser cutting is that we can cut very intricate designs due to obviously it being computer controlled. We can create those designs in a CAD model and then easily transfer them into a real world working prototype. The cons is that it is very high energy use to run a high power laser. And there is also the potential of fumes being produced, which can be unhealthy if not extracted properly, or potentially damaging to the local environment. And also, it can create burnt edges on some materials, such as, uh, as birch wood. Like if you're using a birch ply in the laser cutter, you'll probably get a burnt edge on that, which is not perfect. Again, it's fine for a prototype, but it's not something that you'd want in a finishing product. Uh, and also, if incorrectly calibrated, it can also create some issues and burn other materials such as acrylic, or and create black spots, which we really don't want. So, what is the process you need to describe in your exam? Well, there isn't really a process, but I've created one anyway in case you are asked to describe it. Well, the process is to firstly create the CAD file that you are cutting and upload it to the laser cutter software. You then secure the material to the cutting bed and select the cutting settings you need. So that's the speed and power essentially of the machine. Then you'd start the laser cutting process, or activate the machine, and just monitor the cut to make sure that it's working correctly and that fumes are being extracted. Then you just remove and inspect the final piece. So our next process then is creasing. Now this might look like a little bit familiar if you are paying attention. This is the same diagram for die cutting, and it's because they've been combined in the textbook. So creasing is essentially a method of creating a fold line in a piece of paper or a board by applying pressure with a creasing die. Sorry, I'm tweaking out there for a second. So basically the uses of creasing is like for folding cartons or greeting cards. So like when you get a greeting card and it's got a fold line down the middle, it's probably been done by a creasing die. So the pros of it is that you can create some really clean folds that would be difficult to do by hand, and you can prevent any cracking of the material. It's also very good for mass production because it's quick, repeatable, and accurate. Cons of it is that it can actually wear out over time. This is less accurate for a creasing rule and more sort of so for a cutting rule. But in certain circumstances with a creasing rule, we can have issues with long-term longevity just from continued use. And also, you're limited to certain thicknesses with how you can crease things in this particular way. And it also requires alignment, so you have to align the material with the creasing die very accurately, which can sometimes be difficult. Think about, again, the greeting card analogy. If you had a line on your greeting card that wasn't straight, that would be a big issue. So the process you need to describe in your exam is very similar to die cutting. You're basically designing the locations of the crease on the creasing rule die. And then you'd attach the creasing die or wheel. We're going to just ignore that or wheel part because it's not actually necessary or needed in the specification at all. So ignore any other form of creasing. We're just looking at the creasing die. And you'd position the material on the machine bed. You'd align the die with the crease lines. And then you'd apply pressure to create the crease. Now, you could apply pressure by saying you'd operate a hand crank with a clamp on it, or using an electronic clamp or hydraulic, electronically controlled clamp. You then remove the material carefully, or press, sorry. You would probably say press, not clamp. And then you check your creases for accuracy. Next, we're going to look at the bending process. So that can best be described as a process that deforms a material, usually a sheet of metal or, in this case, board, along a straight axis to create an angled shape. So the uses of this could be for folding box lids or metal enclosures. So some of the benefits of bending is that you basically can quickly shape a flat piece of material into something useful. There's no heat needed in this particular form of the process, and it can create quite strong folds. The risks or cons of it, though, is that you do have a risk of cracking the material, especially if you bend it too sharply. That's less so with boards, more with metals, but in certain more brittle kinds of boards that can happen. You can also create quite significant tooling marks since there's a singular point of pressure on the material. And there is a limitation to the angle due to the sort of, as we already mentioned, the risk of cracking, but also because there's a limitation of the actual machine getting in the way. So, and that would be described as a sort of mechanical limitation of the process. So the process you need to describe in your exam is firstly to measure and mark the bend line on your workpiece. And then you'd secure the material into what we call the folding table. And that's this process, that's what we're using. And then you'd align the bend material with the bending edge and apply the force using the brake or press, and then bend to the required angle. So you're using that as a sort of as a fixed point to bend it to the required angle, and then you'd release the material. That was very quick. That was papers and boards. Now we're going to look at polymer processes. So first polymer process is vacuum forming, which can best be described as a thermoforming process that shapes heated plastic over a mold using vacuum suction. So that's very important there, vacuum suction. Obviously, it's in the name, but people get thermoforming and vacuum forming confused. So just remember, vacuum forming is when you have that vacuum, and that's what's pulling it over that mold. So the uses of this are probably for packaging, most likely, in some scenarios like yogurt pots, but also for like tools, where you've got the packaging where it's like a translucent piece of plastic that's been wrapped to hold the tools in place using a vacuum forming process. The pros of it is it's very low cost, very cheap to do, and it's also quite a simple setup. If you have the machine, obviously it's quite a high setup cost to get a vacuum forming machine, but once you have one, it's very easy to swap out molds, and that requires very little tooling. Can be created with a CNC router, or even with a 3D printer if you had the necessary if you had a 3D printer that could print a higher temperature thermoplastic than what you're using in the vacuum former. It's also quite quick, very quick process. The only time constraint really is the material being heated. The actual vacuuming itself happens very quickly, and the material also cools very quickly. The cons of it is that you do sometimes have limited detail because of overlapping edges. There's just not really much you can do if there's an edge or a cavity that overlaps and the vacuum can't access it. It can also sometimes lead to thin edges around sharp corners, which can lead to the material being brittle or not perfectly fitting. And there's also some waste. Pretty much every time you use a vacuum former, there'll be a kind of waste where you have to cut around the edge of what has been formed, which contributes to waste, which is pollution if not recycled properly. The process you need to describe in your exam is to place the sheet into the machine and heat until it's flexible. You'd raise the mold into the softened plastic, and then once it's raised into the plastic, you'd activate the pump, which will pull that sheet down and secure it over the mold, making sure we get all that detail. And then you'd allow for the plastic to cool and harden before you remove it from the mold. And you can lower that mold and remove the formed part, at which point you can then remove any excess plastic. So thermoforming, as I said, often confused with vacuum forming, but the key thing here is that it is a process where a heated plastic sheet is pressed against a mold using only mechanical pressure to form the shape. So just remember, it's only the mechanical pressure in thermoforming. There's no vacuum. There is an air escape typically at the bottom of the mold, but that's simply so when you apply mechanical pressure, there won't be any sort of trapped air bubbles underneath that positive mold. And underneath the plastic sheet. So the pros of thermoforming is that obviously you don't need a vacuum, which means there's a lower cost of tooling, because you don't need to create any kind of complex. You don't have to buy a vacuum former. Essentially, you can use basically anything. You could just simply create a thermoforming jig in-house quite simply with a workshop, but it also can give you some great surface detail, which is nice. Probably not as much as a vacuum former, but because of obviously using mechanical pressure, if you have a cavity, it's more likely to be impressed because you don't need it to have an escape for the air to get through. Some uses. Oh no, we've already gone over uses. I think, have we gone over uses? You could use it for like food trays, for example, or shampoo bottles. I've gone sort of over course with this one, but it also has quite fast cycling time because you don't need to wait for any vacuuming to happen. And also you can remove the positive mold immediately once the indentation has been made. You don't have to wait for the material to cool. It's probably best practice to do that. The cons of it is that you can only really do it with thin sheets, quite similar to vacuum forming. It's probably not going to be used for a permanent product, more likely to be something packaging. And also, there's the issue of edge thinning, which is already mentioned with the other one, where, around tight corners, the material will tend to get a little bit thinner. Sometimes it can lead to failures in the packaging or the material where it gets brittle. It's also a limited strength. So in this one, you're limited by how much mechanical pressure you can apply to the positive mold, which obviously then limits the amount of detail you can have imprinted into your plastic. The process you need to describe in your exam is essentially load the plastic sheet into the machine or jig and heat it until it's pliable, at which point you would then move the sheet over the mold and press the sheet into the mold with a pressure plate or positive mold. It allowed for the plastic to cool and set before releasing pressure and removing the part, at which point you can then trim off any excess material. Next, we're going to look at calendaring. So calendaring can best be described as a process that forms plastic into a thin sheet or film by squeezing it through heated rollers. So some examples of products that can be created with calendaring is like vinyl flooring or any kind of plastic sheeting, really. So we can actually use calendaring in combination with the previous two because they require a sheet material. Pros of calendaring is that it's very easy to create a smooth, quickly creating a smooth finish on a material with a precise thickness due to having the rollers fixed in place. And it's also a continuous process because we can just continually put material into the feedstock and have the rollers pushing it out into a flat piece of material. So the cons of it, though, are that it is quite high setup cost. So you have to invest into the machinery to have all of these rollers rolling the material into the sheet stock. And also it only creates flat sheets. So obviously we can do something after with it, but we're just purely using the calendaring process. We're only going to be able to create flat sheets of material. It also needs constant monitoring to ensure there's no jams or blockages in the system, because that could seriously be damaging to the equipment and really costly, as well as also removing it and like sort of just not creating anything quality. So the process you need to describe in your exam is to heat and soften the plastic in the feedstock, feed the plastic into the roller system, at which point the plastic is compressed between the rollers and the rollers are adjusted for the thickness of the material. So the sheet exits, called the sheet stock. I've probably just mentioned that, saying this sheet stock exits and it cools after it's exited the rollers. There you go. So the next process is line bending. Line bending, I'm sure, again, it's another process where you probably used it for your NEA at one point if you used acrylic. It's a process that bends a thermoplastic along a straight line using a heated element. So the uses of this would be for like acrylic stands or display holders. That's just the two I thought of. But there's plenty of examples of ways you could use it. Pros of it is that it's a simple setup, and you can accurately bend it along your bend line. And there's also no molds needed, which means it's very versatile. So once you have a line bending piece of equipment, you don't need to create new molds to do different kinds of line bends or different angles. You can just simply reuse the same piece of material, or same machine, sorry. The cons of it, however, is that it is quite slow because you obviously have to wait for that material to heat up, and also it's kind of a manual process. You also bear the risk of overheating the material and potentially melting it into the heating bar, or burning the surface of the material. Can happen with acrylic as well. And also it's limited to straight bends. And by that, I mean the heater bar is in a straight profile. It's not going to be in any sort of unhorizontally continuous profile, and line bending wouldn't work for a non-horizontally continuous profile. So just remember that is a limitation of line bending as a process. So the process you need to describe in your exam would be to mark the bend on the plastic, preferably, so you know exactly where you're going to bend it. And then you'd place it over the heating element or heater bar. You'd heat the plastic until it softens, and we'd then remove it from the heater, at which point we could then bend it to the required angle for what we need. And then you just hold it until it's cooled down enough to set. So the next process is laminating. This is called the layup process specifically. So we're going to be talking about more like a composite kind of layup, more like, that form of laminating, not like wood laminating when you're putting veneers together. We'll talk about that later. So it can best be described as a process where layers of material are bonded together with resin to form a strong, lightweight composite. So the uses of this could be in really anything, but anything that's made out of a composite material. So boat hulls, car panels, anything where we're using a composite to make a part nice and light but strong. The pros of it is that it creates a strong and lightweight part. That's kind of just the pros of composite materials, really. But laminating specifically allows you to create a very custom shape using a limited amount of tooling and using a lot less material than other kinds of composite processes, which means we have less material waste. The cons of it is that it's very labor intensive. I know, because I've done it myself and it takes a lot of time. And there's also a lot of time to wait around after you've done the process, because it just has to cure in the open. You can't put it in an oven or anything like that. It just has to cure out. It also requires ventilation, because obviously, resin, once it's hardened, heatens up, might create fumes, depending on what kind of resin you're using. So the process that you need to describe is very simple. You're preparing the mold surface. That would be by putting a release agent, which is the second step, actually. Preparing the mold surface, which would be then just sanding it, making sure it's smooth, and then applying the release agent to the mold, which would be some kind of like wax. Then you'd lay the first fiber onto the mold before rolling on some resin into those fibers. And then you just simply repeat that with as many layers, a bit like making a lasagna, and you'd leave it to cure and harden. In some scenarios, you could also potentially describe creating a vacuum bag for it to ensure that all of the layers are compressed down together. That's what we did when we did a layup, but I haven't mentioned it here because it's not necessarily that important to mention. Step 7 is just an optional thing, really, just removing it from the mold and trimming the edges. It's not really part of the laminating process, but I always like to mention it in there just to show the examiner I'm thinking holistically. So injection molding is the next process, not to be confused with blow molding. Often get confused for some reason. They're not even that similar, but it can best be described as a process where molten plastic is injected into a mold to form a complex, high-volume part. So what I mean by high volume is that it is thick material, and the uses of it would be for like a bottle cap or phone case. That's something quite interesting I realized earlier when I was making this, is that if you ever get injection molding and blow molding confused, think of blow molding as the process that creates the bottle, whereas injection molding is the process that creates the bottle cap. So the pros of injection molding is that you can create some really high volume output, which means we can basically create as many, it's suitable for mass manufacture, is essentially what I'm saying. And also it's a very high level of detail because we're injecting that plastic so highly pressurized into that mold that we're filling the mold entirely and creating a super accurate shape. And we also have a very little amount of waste because we're only injecting the amount of material we need. There's no sort of like sprues we need to cut off after the fact. or there might be a sprue we need to cut off after the fact, but not a significant amount of wasted material. The cons of it, however, is that there is a very, very, very high setup cost with injection molding, which makes it, not very applicable for bigger pieces and bigger parts. Although there is some larger injection molded things like larger injection molded products such as like school chairs, for example. But typically injection molding is more appropriate for a smaller part because of how expensive the molding is to create, because it has to be a heat treated piece of metal. This can lead to very long lead times. What I mean by lead time is essentially the time it takes for us to go from the start of the project to the finishing point of a project, similar to sort of like our float time. And in this scenario where we're using injection molding, that is a very long time because of the difficulty of creating the molding and the tooling. And even after you've paid all that money to get the mold, it can wear out over time, which can lead to us having to replace it, which is obviously quite high cost. So the process you need to describe in your exam is basically loading the pellets into the hopper, and then in which point they are heated in a barrel until they are molten and liquid. Then they are injected into the closed mold at high pressure, and we wait for the plastic to cool inside of the mold so that when we don't remove the mold, it can just fall out as a liquid. And then we'd open the mold and eject the part. And if you want, you can also write that you would then inspect the finished product and trim off any excess, such as like a sprue where it was injected if needed. So blow molding is the next process. And this is basically a process where a hollow plastic part is pushed into a mold using high pressured air. So in this scenario, it's confusing because in both scenarios you are injecting something, but in the first process you are injecting the plastic, in the other process you are injecting the air. So the uses of blow molding, as I mentioned earlier, is that creating that bottle, but you could also create other things which are just large cavities, such as fuel tanks. The pros of it is that it creates hollow parts. That is kind of a pro, I guess. And it also is a very fast cycle time, which means we can do it very quickly, which makes it very appropriate for mass manufacture. There's also a low material cost or low material use, and I guess a low material cost because we're using a thin piece of material stretched out into a larger area, which makes it very cost effective. The cons of it is that it is limited to hollow shapes, of course. We can always fill it in, but it's not necessarily something that would be... wouldn't go to blow molding if you are going to fill it in. And there's also less detail than injection molding because we are relying on the sort of pass and tube to fully fill out that area with high pressure air, whereas when we're injecting it fully with plastic, we can be sure that it's filling all parts of the mold. There is also some kind of waste from having to trim off the edge of the parson once it's been molded. The process you need to describe in your exam would be that the extruded tube of molten plastic called, not the parson, sorry, I've been calling it right, is the parison. Or it's something like that. I don't know the exact pronunciation, but it's on the screen. And then you'd clamp around the parison and blow air into it to expand it into the mold shape. And once the plastic has taken the shape of the mold, you'd wait for the plastic to cool and harden, and then you can eject the part and trim any of the excess. Okay, next we're going to look at rotational molding, and that can best be described as a process that forms hollow parts. So similar to blow molding, it's forming a hollow part by heating and rotating a mold filled with plastic powder. So parts that we're creating with this would be like water tanks or traffic cones, anything that's quite large where blow molding wouldn't be as appropriate. So the pros of it is that it creates a very even wall thickness, especially if the mold is being spun on multiple axes, and it also leaves us with no seams in the final product, which means we have a stronger overall product. And there's also quite a lesser tooling cost because it doesn't require any sort of special materials to create the tooling. The cons of it is that it is quite slow. It takes longer for the plastic to fully fill out the inside of the mold since we're relying on gravity. Uh, and there's also a high energy use because we're having to rotate that entire molding. And there is also limited detail again because we're just relying on gravity, which is not very strong to go over parts of the mold, which means that really we can't create that much details in the molding. So the process you need to describe in your exam would be basically adding plastic powder or pellets into the mold and then closing it securely, making sure it's properly shut so there's no leaks, and rotating the mold on 2 axes for even distribution, and heating it so that the plastic melts and coats the interior of the mold. Then you'd continue rotating it as it cools to ensure that it doesn't sort of flow down, and you'd open the mold and remove the parts. Because you have to keep rotating it as it cools as well, that's part of the reason why it takes a bit longer than some of the other processes. Then you'd trim off any excess material if needed. Next, extrusion. So extrusion can best be described as a continuous process where molten plastic is forced through a shaped die to form a long, uniform profile. So examples of products we create using this would be like pipes, so example like PVC piping, or window frames, anything with a horizontally continuous profile. So the pros of it is that we can create something with an even wall thickness and no seams, and it's quite a low tooling cost as well because we only actually have to create the die shape. We don't have to create an entire mold. Cons is that it is quite slow because obviously you just slowly extruding the material through it. It's not like an instant process, and it is quite high energy usage. There's also a limited amount of detail that we can have in the profile and still have the material extrude evenly. So that's another limitation with it, is that we're limited in detail, not only in the horizontal, not only in the profile shape, but also in the fact that it has to be a horizontally continuous profile. So the process you need to describe in your exam is essentially just loading plastic pellets into a hopper, at which point the plastic pellets are heated until molten. The molten plastic is forced through the die, and then the plastic is shaped into a profile according to the die, and then it will cool essentially with air since it exits straight from the die, typically onto a conveyor belt, and it can be cut then to the desired length and inspected to ensure quality. Next, compression molding, best described as a process where heated plastic or resin is placed into a mold cavity and compressed to take the mold shape. So quite similar to what do you call it? Thermoforming, except in this scenario we're not using a sheet of plastic. So the pros of it is that it can create very strong parts because we're using a thicker piece of material in this scenario, and also there's less waste because we're not having to cut off any excess. There's also probably a good surface finish on it because we are just compressing it down, and polymers are usually self-finishing. Cons is that it can have quite a slow cycle time, take a long time to compress the material down, and there is a lot of pressure needed to compress that hot material down since it's not going to be a molten piece of plastic. It's just going to be heated to a point of being moldable. So there is also a limited that comes with the limited to a simple shape, limited in detail essentially with what we can actually press it into because it's not molten, so it's not going to fill out a mold. The uses of this would be for like electrical fittings or car bumpers, so something where it's just quite a simple shape, not too high in detail. The process you'd describe in your exam, sorry, 1 second, would be placing a preheated plastic charge into the mold and closing the mold with pressure. You then apply heat to shape the parts. So that's basically you're applying the heat and the pressure at the same time, and you'd hold the material until it cures or cools. Then you'd open the mold and remove the molded part. And then if there is any excess material that's gone around the molded the molded press, then you would cut that off. Next, we're going to look at metal processes, starting with metal forming processes. So firstly, we have press forming. Press forming can best be described as a process that uses that shapes sheet material by pressing it between a die and a punch. For example, we've got like car body panels and kitchen sinks, typical things that are being made with press forming. Pros of it is that we can create some really accurate shapes and very quickly. We just press it onto the next. Brilliant for mass production, but it's also good for large parts since we're not using any particularly complicated tooling. Cons of it is that there is actually high tooling costs. I know I just said it's not particularly complicated, but it can be quite expensive. There's also a risk of cracks in the material if we're press forming a particularly brittle piece of material, something to take into account. And is also limited to only ductile metals. So, as I mentioned, something to take into account when evaluating whether not to use the press forming process would be the kind of material we're using. So the process that you'd use is placing the material. The process you need to describe in the exam would be place the sheet metal onto the die and align it above the punch die, which is the thing that applies the force. So we got the female and the male die, or the punch die, and then you'd activate the press or use the hand crank press to lower the punch, and at which point the metal would be deformed into the shape of the die, and we can release pressure to remove the formed part. And at that point, we can then trim any excess if needed. The next is spinning. So spinning is best described as a process that shapes metal into a hollow or symmetrical form by rotating a disc and forming it over a mandrel. So examples of this would be like lampshades or cookware, something that's round typically, since a mandrel is essentially a round boss form, which means we are limited in shape here. So that's one of the cons. But the pros is that it is very low waste because we don't usually need to cut off any excess, and there's not very much material we need to use. It's good for round parts, as I mentioned, because that is what the mandrel is. But it also creates quite strong finished parts because we're not having to use anything with a particular high ductility. Because we are just forming it into this process using a roller tool and some spinning. So the cons of it is that you do need a skilled operator to use the machine who knows how to do spinning, which requires experience, increases the cost of having to do this process, and then therefore the cost of the final price of the final product. It's very slow as well, which again increases our lead times. And it also, as I said, is limited to the shape because of what the mandrel actually has and what it is. So the process you describe in your exam, and you could actually have to describe this, would be mounting the metal disc onto the spinning lathe, at which point you then secure the mandrel with the desired shape that you want. And you'd start the rotation of the disc and the mandrel on the lathe. And then you'd simply use a roller tool to apply the pressure to the surface and shape the material over the mandrel. You'd then smooth using the roller tool to make sure it's all consistent and remove the formed part once complete. Next, cupping / deep drawing. Well, they are quite similar, so I've put them together, and your textbook does too. So it can best be described as a metal forming process that uses a flat metal blank and forms it into a cup shape using a punch and die. So, for example, like aerosol cans or battery cases. The difference between deep drawing and cupping is that in deep drawing, the depth of the press exceeds the diameter of the press. So that's essentially the difference. That's all it is. That's why we usually group them together. The pros of it is that it can create some seriously strong shapes and repeatably do that with every material because we're just using the same piece of tooling. It also leaves us with a smooth finish since we're not having to cut or remove any excess. And the cons of it would be that we need quite a lot of pressure to create that cup shape and push it into the die, which can be expensive, energy cost. There's also a certain amount of tooling wear due to the high friction required, and that could be expensive if we have to replace the tooling. There's also limited to a shallow-ish form because we can't create something that's super deep. It just wouldn't work with the molding process. So the process you need to describe in your exam would be placing the metal blank over the die cavity, aligning it with the punch above the blank, and then activating the press to drive the punch downward, or using a hand crank press. As I mentioned before, you can always use that alternative, potentially score some more marks, and then you'd allow the metal to flow into the die to form the cup shape. And the die is, when I say metal flow, is kind of not the word I would use there, but sort of allow the metal to be deformed into the shape of the die and the cup shape. Then you'd release the punch to eject the part, or in some circumstances, the die will just have a hole at the bottom of it, so it will just simply fall through into a parts bin. Next, the forging process is a process that shapes metal by applying compressive forces using hammering or pressing, often while hot. So this would be for strong. This is when we need something that's very strong with a high tensile strength, like a wrench or a crankshaft. So the pros of it is that we are creating some super strong parts here with high tensile strength, and we're also creating something with a good grain structure, which means we have a very high durability. So this is all kind of the same thing, really, those pros. But that is basically the main benefit of forging. The cons of it is that it is very labor intensive, especially if it's being hammered instead of using some sort of a process. But even still, it's labor intensive, and you need an experienced operator, which increases the cost. And if you are using a hydraulic press or a non-automated press, something that's not you're not hammering it, you are using an automated press, then that is going to seriously contribute to some energy costs, and that's got environmental and, as I mentioned, cost considerations. And we're limited to the shapes that we can create with this process, really. So the process you describe in your exam would be heating the metal billet. You have to remember that, billet, to the forging temperature, which will just be hot but not molten, but malleable, to a point of being malleable. Then you'd place the billet on an anvil or die and strike or press the material. So again, it's striking with a hammer onto an anvil or pressing the material in a hydraulic press to shape it. You then reheat if necessary and repeat. And then once you've created that shape, you would just cool the forged part. You could potentially cool it very quickly and create something tempered to increase strength. Next, we're going to look at drop forging. Drop forging can best be described as a process where a heavy hammer is dropped onto a heated metal to shape it within a die. So it's very similar to the previous process, except in this scenario, if I go back for a second, you can see that we're looking at a flat die on the bottom, but in this one, we are looking at a die which is shaped on the bottom. So the lower die has some kind of mold to it. So this can be used for creating more complex parts, like in complex shapes that still need to be really strong and have a high tensile strength, such as gear blanks. Or again, you can use it for parts like we use normal forging for, which is like crankshafts or like wrenches. The pros of it is that it's high precision and it creates really strong parts, as I mentioned. For forging, it's the same thing here. Another advantage over forging, though, traditional forging, is that it is a very fast cycle because we are pushing it directly into the shape that we want. We don't have to continually repeat the process until we have that shape. The cons of it, though, is that we need to create a really expensive piece of tooling that is heat resistant and can withstand the high heat temperature of the metal billet. And there's also a lot of noise and vibration that may create inconsistencies within the material and the part. And we're limited to a certain size because of the size of the press, but also because of the expense of the tooling, which makes it inappropriate for sort of like larger parts. So the process we'd use or describe the process we describe in the exam would be to heat the metal billet to the forging temperature, place the billet in the lower die, and align the upper die above the billet. Drop a heavy hammer or press onto the upper die, which means the metal will fill the cavity and create the shape. Then we just simply remove the forged part once cooled. So next we're going to look at the bending process, which we've already looked at the bending process, but in this one we're looking at metal bending specifically. So it can best be described as a process that deforms a metal sheet or plate along a straight line to create an angle shape without breaking. So the uses of this would be to create like brackets, like a right angle bracket for a shelf, or to create metal enclosures, or as I mentioned earlier, like a metal lid. So the process, let's start with the pros and cons. So the pros of it is that it is very fast and very simple. There's almost no material that you need to remove afterwards, which means less waste. And also, it's good for thicker sheets of material because we're not having to cut it necessarily. We're not using, it's not like a die cutting process. We can bend thicker pieces of material with this. The cons of it is that there is obviously the risk of cracking depending on how ductile the material is. And also there is that spring back effect. It's not just the ductileness of the material, it's also the shear strength of the material. But the spring back effect particularly refers to how material that could respond after being bent back into its original shape and return to its original shape. And there's also a limit to the sort of tooling that we can create to use to create particularly unique parts with this process. The process you describe in your exam would be marking and measuring a bend line, placing the metal sheet into the bending machine, align the bend line with the bending tool or punch, and then applying force to bend the metal, holding it until the desired angle is reached, and raising and removing the part to then inspect the bend for accuracy. Next, we're going to look at rolling, which is a process that reduces the thickness of a metal and changes its shape by passing it through rollers, similar to calendaring. The pros, God, I'm losing it. The pros of a process like this is that it is very high volume, which means we can do it with a lot of material very quickly, and it creates a consistent thickness of material due to the fixed rollers. It's a very efficient process with basically no waste. Since we don't have to remove any excess or anything in this particular part of the process. There might be something down the line we have to remove the excess, but particularly within rolling, it's very efficient. Cons of it is that there is quite a high equipment cost to create those expensive rollers and also to get them set up correctly. And there's a limited to simple shapes because we're only really creating a horizontally continuous piece of material. A flat stock form, that's all we can really do. In just with rolling. There's also a possibility to create surface defects if our rollers are particularly worn or if the material we're using is not particularly ductile. So the process that you'd use for this would be, or how you describe this in the exam, would be heating the metal so that it's ready to be rolled. This is in particularly for hot rolling. You don't necessarily need to heat the material. Some materials you won't need to heat, like for example copper, you could do without heating. And then but just mention that as well, just to gain some marks. And you'd feed the metal between the rollers, which will apply pressure and shape the material into thinner metal. Shape the metal into a thinner form, and then you could pass it through multiple roller sets to create the desired thickness, and cool the metal if it was hot rolled, and then at which point you can then cut it to length. Next, we're going to look at some casting. So firstly, we've got sand casting, which can best be described as a process where molten metal is poured into a sand mold to create a shaped part. So we would use this for creating something like an engine block or pump housing. And of course, the benefit of this is that we have a seriously low tooling cost because we don't have to create some complex mold. We're just using sand, which means it's great for prototyping, but it's also suitable for larger parts because we don't have to create that expensive molding. It creates some opportunities for flexibleness in how we're creating our shapes, so we can be flexible about that. That's a weird way of describing it, but I'll put it like that, which basically means we have more options over how we can shape the mold. And the cons of it would be that we kind of create a rough surface finish because obviously it's sand. It's not going to create a smooth finish on the part, but that's fine. It should be fine because, of course, for things like engine blocks, you don't necessarily need a smooth surface finish on the exterior. And also, there's a low dimensional accuracy because obviously the sand can move and not exactly form to the shape of the blank, so it's not entirely accurate. And there's also a possibility for it to be quite slow because, of course, we're having to recreate the mold every single time because we are essentially destroying the mold to remove the part. The process you'd have to describe in your exam would be that the pattern is created of the desired shape. So, for example, an engine block. And then the sand is packed around the pattern and a sprue pin is used to create to form the mold. So a sprue pin is allowing us to pour the material in. We then remove the pattern and the sprue pin, leaving the mold cavity, and we can pour our molten material into the mold through the gap left by the sprue pin. We'd do 2 sprue pins, so we'd have a vent so the air can escape as well. And then once the molten metal has filled the mold, you'd allow it to cool and solidify before breaking up the sand to retrieve the cast. So next we're going to be looking at gravity die casting. So this can best be described as a metal casting process where metal is poured into a mold and by gravity into a reusable mold. So not like sand casting where we're using something that is a one-time thing. It's a reusable piece of molding, which forms a which forms a part. So we can use this for creating something like an engine block or a pump housing, quite similar to sand casting. The pros of this obviously is that you have a lot better dimensional accuracy than something like sand casting because we are creating a direct mold, not relying on the accuracy of the sand. And also because it's reusable, it's a lot quicker, faster process, better for mass manufacture. Doesn't really suit a prototyping approach though. So something you could use as evaluation. Another benefit is that it is a better surface finish than sand casting because, of course, we're using a smooth piece of molding, so we're going to end up with a smooth surface material. Cons of it is that it's a very high tooling cost because, as I mentioned earlier, sand casting, there's practically no tooling cost because we're using sand. All we have to do is create our pattern. Whereas in this scenario, we're having to create an entire mold, typically out of some kind of heat-treated metal, which is very expensive. We're also limited to simpler shapes, just due to having to create it out of that high temperature metal. But in some scenarios, obviously, we can create more complex shapes, so I'm not sure if that's entirely accurate. It was also slower to pressure slower than pressure casting, because we are relying on gravity to fill the mold. So the process you need to describe in your exam would be preheating the metal die, and at which point you would then place the die into the casting machine. So it has to be heated. Otherwise, the metal will simply cool and not fill the mold entirely. Then you'd pour the molten metal into the die, cavity by cavity, at which point you'd then allow the metal to cool and solidify within the mold, and open the die to remove the casting and trim any excess material off, as well as inspecting and the finishing cast. Next, we're going to look at pressure die casting. So pressure die casting is when we use molten metal that has been injected under a very high pressure into a reusable mold. So similar to gravity die casting, except we're just injecting that material, a bit like injection molding for plastics. And we can create engine components, but we can also create jewelry, which is nice. Pros of it is you have very good dimensional accuracy, again, because we're using a tooled piece of molding, and it's a reusable mold, which means it's quick to reuse, unlike sand casting. So it's more efficient, basically. And again, we get that better surface finish because we're using a smooth piece of molding. The cons of it is that, again, very high tooling cost. It's the same pros and cons, isn't it? It's the same pros and cons of gravity casting, except, of course, in this scenario, the pro against gravity casting is that it is actually faster than gravity casting. The process you need to describe in your exam would be heating the metal until it is molten, so that is liquid form of metal, and then injecting that molten metal under a high pressure into the closed die, and waiting for it to cool inside of the die before opening it and ejecting the casting, at which point we can then trim any excess material as well as inspect for the quality. Next, we're going to look at investment casting. So investment casting can best be described as a precision casting process where a wax model is coated in ceramic and then melted out and replaced with molten metal. So that's quite a complicated thing there. So I'll just say that again. A precision casting process where a wax model is coated in ceramic and then melted out and replaced with molten metal. So it's quite easy if you look at the process diagram in the top corner to understand sort of what's going on here. The uses of this would be for turbine blades particularly, but also again for jewelry, something that's very small, needs high accuracy. And the pros of it is that it creates really excellent detail and allows us to have very complex shapes with a very smooth surface finish. So this is the best of both worlds. This is like your sand casting, and which allows for that very complex shape, but also with the smooth finish that you don't get with sand casting. The cons of it, however, is that it is very expensive because it's a very time-consuming process, which again contributes to a long lead time. And it's also quite labor-intensive because there's a lot of steps to it, and it definitely cannot be fully automated. It requires some sort of labor to run the process. The process you'd need to describe in your exam would be creating the first step would be creating a wax pattern of the part, and then attaching that wax pattern to a central sprue, at which point you can then dip in a ceramic slurry to form the shell. And then once you have that ceramic shell, you can dry. You wait for that ceramic shell to dry and repeat that to increase the strength. At which point you can then heat up that ceramic shell to melt out the wax from the center, and then you can then pour into that ceramic shell the molten metal and break the shell to finish the casting. So the next one is low temperature casting. For example, pewter. This is the one we're going to be talking about mostly, but it's also highlighted like that in your specification and in the textbook. It's particularly with pewter metal, and that is how you pronounce it. I know it's a bit weird. So the description of the process is a casting process using low melting point metals like pewter poured into simple molds at relatively low temperatures. So the uses of this is, as I mentioned, for other things, it's pretty much prototyping. Is the main use for this. But it's also for creating decorative designs, something where you don't need extremely high strength because pewter is not a particularly high strength metal. So the pros of it is that it has some very low energy use. Don't need a lot of energy to heat up and melt the material into the metal into a molten form. There's also very simple equipment. You don't need to create expensive casting. You can use, MDF for the mold, and you probably will use MDF for the mold, especially because this is very commonly used in like DT departments to sort of teach a simple molding process. It's also very good for small runs because, as I mentioned, it's very cheap to create the molding because you don't need to create it out of any particularly heat-treated metal. You can use, as I mentioned, some sort of manufactured board like MDF, which makes it a lot cheaper and a lot simpler to create our molding and better for rapid prototyping, or not particularly rapid prototyping, but prototyping. The cons of it is that there is a limited strength, obviously, to the material because pewter, as I mentioned, is not particularly strong, and it's not suitable for high stress parts because it's not very strong. There is also a lack of durability in the mold, particularly if you're creating the mold out of something like MDF. It's probably not going to last for that many uses before potentially failing. And the process you need to describe in your exam would be preparing the mold, usually metal or silicon. I've written here, but it's more likely to be metal, silicon, or MDF. Potentially, I wouldn't even mention silicon because it's just not as common. And then at which point you'd heat the pewter until it's melted, which is around 230 degrees centigrade, and pour the molten pewter into the mold, allow it to cool and solidify, remove the casting from the mold, and clean and polish the part, at which point you can then inspect it for defects. So next, we're going to look at metal processes in addition and fabrication, which is just the next point on the specification. First one we're going to look at is MIG welding, which is metal inert gas welding. And this can best be described as a welding process that uses a continuous solid wire electrode fed through a welding gun with an inert gas shielding the weld area from contamination. So we use this in automotive repairs, but also construction steelwork because it is very fast. This is the process. It's very fast. It's very good for thick material, so it's very strong. And there's minimal cleanup. So there's not a lot that you have to do once you've actually welded it. It kind of requires some shielding gas, though. Well, as I mentioned, because you need that metal inert gas, which can increase the cost of having to do it, and it's not ideal for outdoor weather conditions. So you can't really do this in the rain, and also the cost of the equipment is higher than other welding methods. The process you describe in your exam would be preparing and cleaning the metal surfaces, and then you'd set the welding machine's parameters, and just controlling it. It'd probably be computerized. You'd then connect it to a ground clamp to the workpiece and hold the welding gun at the correct angle. You'd then pull the trigger and use to feed the wire and gas and steadily move the gun along the joint. Once you'd finished, you'd then inspect and clean the weld. Next, TIG welding, or tungsten inert gas welding. This can be described as a welding process that uses a non-combustible tungsten electrode to produce precise welds with inert gas shielding to protect the weld area. So again, we're using a protective gas, but in this scenario, we're using a tungsten electrode and a filler rod. So the uses for this would be basically aerospace components, something where you need seriously high strength and low failure, but also for stuff like stainless steel fabrication. Pros of it is that it is super high precision. It creates very clean welds, as I mentioned, with low failure rate. And it works on thin metals, which, as I mentioned, is very important in aerospace because you need to be low weight, so light. The cons of it is that it is a slower process than MIG welding, and it requires a very experienced operator. It's more difficult than MIG welding, and it uses more expensive equipment, which increases cost. The process you described in your exam would be cleaning and preparing the metal surface, set the welding gun to the machine parameters, and strike the arc using the tungsten electrode. So that's the one thing, the electrode is going to be positively charged and the workpiece is going to be negatively charged, which is how we're getting that arc. You then feed the filler rod manually if needed. You probably will need to be manually, to be honest, and maintain a steady arc and travel speed along the joint, and then shield the weld area with the inert gas. Once that's completed, you can then inspect and clean the weld. The next one is spot welding. So spot welding can best be described as a resistance welding process. So we're using the heat of friction to join metal sheets by applying pressure and electric current in small spots. So this can be used for like car body panels to attach them together, but also for like metallic furniture, where we don't want to have a particularly, you don't want to see a weld, really. You want to have something that's like nice, neat, and looks clean. So the pros of it is that it's very fast, then there's no filler needed, no filler material at all. And it's also good for thinner sheets of material. So similar to TIG welding. Cons of it, though, is that you are limited to overlapping materials. And there's also a very shallow weld depth. So whilst it does work well with thin sheets, it doesn't work particularly well with thick sheets. And it requires specialized equipment. The process that you describe in your exam would be aligning the sheet metals to be joined, positioning the welding electrodes on both sides, and then applying pressure to clamp the sheets together. At which point you then pass electrical current through the electrodes, which will generate enough heat to melt and fuse the metals at that spot. You then maintain the pressure until the weld cools, at which point you can then remove the electrodes and inspect the weld. Next, we're going to be looking at oxyacetylene welding, which is a welding process that uses a flame produced by burning acetylene with oxygen to melt and join metals. So this could be used for pipe work, but also for certain metal repairs. Pros of it is that it is a very portable setup and is good for thick metals. It's also very versatile, since we're not relying on any particular type of metal. We're just using a filler rod. But the cons of it, though, is that it is a lot slower than electric welding, and it requires careful gas handling because the gases are explosive and flammable, and there's also less precise control than using an electric welder. The process of it that you'd need to describe in your exam would be setting up the gas cylinders and regulators, igniting the acetylene and adjusting the flame with oxygen, cleaning and preparing the metal surfaces, at which point you can then heat the metal edges with the flame until molten, and add the filler rod to, if needed, to complete the weld, and then move the flame along the joint to fuse the metals. Next, we're going to look at soldering, which can best be described as a process that joins metal parts by melting a filler rod, or filler metal, in this example, solder, with a low melting point without melting the base metals. So this is typically used in electronics, but also in plumbing joints, where it's quick and easy to do it. Although typically for plumbing joints, it might be more likely to be something like brazing, which we'll look at in a second. So the pros of it is that it is a very low temperature process and it's very quick, and it can create a very solid electrical connection which again is very good for electronics, creates less excess heat. The cons of it, however, is that it's very weak as a joint strength, so it's not particularly good for high strength joints, better for electrical joints, as I mentioned. But it's also not suitable for high stress. So that's kind of comes in with the same thing. And it requires a very clean surface to work. Otherwise, the solder will just fall off. The process you'd use describing the exam would be cleaning the metal surfaces that you need to join, heating the area gently with a soldering iron or torch, and applying the solder to the heated joint. You then allow the solder to melt and flow into the joint and remove the heat to let the joint cool, at which point you can then clean any flux residue. Brazing is a similar process to soldering, which is a process that joins metals by melting a filler above 450 degrees C, which allows the joint which flows into the joint without melting the base metal. So we're only melting the filler metal. We're not melting the base metal, which is a common misconception with brazing. We're only melting that filler metal, and that's what's creating the joint. The pros of it is that it is very strong and joins dissimilar metals. So if we're joining two metals that are not the same together, this kind of process would be more applicable. And there's also no melting of the base metals, which means it's just safer for those parts and can result in less failures. The cons of it, though, is that it requires very precise heating to make sure we don't melt our base materials, but also the flux that we need for it can be expensive and is just an extra step in the process. It's also not particularly suitable for a high load because it's just not. It has to be for a smaller kind of joint because we can't apply heat that great across the entire joint. So the process you need to describe in your exam would be cleaning the fit parts to be joined, heating the area gently and evenly with a torch, and then applying the filler metal brazing rod to the heated joint. So obviously we're heating the joint beforehand, and then we're then going to heat the filler metal inside of the joint to allow it to melt and flow by capillary action, and removing the heat to let the joint cool before we can then inspect and ensure the strength and cleanliness, at which point we can then clean off any of our flux residue. Next, we're going to look at riveting, which is quite riveting. So it's a process that joins two or more materials together by inserting and deforming a metal pin called a rivet through an aligned hole. So this is used in aircrafts where you don't want a screw to come undone, but also in just general metal fabrication. So the pros of it is that it creates a very strong mechanical joint, and there is no heat required. So it's a very similar process, very simple process. It's good for dissimilar metals because we're not needing to melt them together. We're just popping a rivet in, and it also creates a permanent joint, which is labor intensive. The cons of it is that it is a permanent joint. That could also be seen as a pro, but also it is quite a large con because it means that we can't disassemble it, and it is very labor intensive to add rivets because you can't do a machine. You can't really do it with a machine. It can create stress points in the material as well due to the high strength of the fixtures. Other than being like, because if it was a weld, it would be a horizontally continuous join, whereas if it's a rivet, it's pressurized fixtures within the material, which can create the stress points. So the process you describe in your exam would be drilling or punching holes in the material and then inserting a rivet through those aligned holes, at which point you can then support the rivet head on one side and deform the opposite end using a hammer or rivet gun. To form a second head to secure the materials. Ignore that one. I don't know what that means. You're essentially just deforming the rivet by securing it on one side and compressing it on the other, which then makes it wider and fill out the hole. and creating a head on the opposite side so that it can't be pulled back through. At which point, once you're done with that, you can then inspect it to make sure that it is tight. We've also got self-tapping screws. So self-tapping screws are screws designed to cut their own threads into materials as they are driven in, eliminating the need to drill the holes. The uses of this could be for sheet metal fastening, but also for plastic assemblies where drilling the holes is not particularly, where drilling the holes would just not be applicable. So the pros of it is that it creates very quick assembly, which means we have no pre-drilling. It's faster, more efficient in some circumstances, and it's also very reusable. It's a reusable fastener, so we can take it out and reuse it again, unlike rivets. Cons of it, though, is that it can crack very brittle materials. So if you try to put a self-tapping screw into acrylic, for example, you might need to be very careful because it can crack the material just due to the stress. Whereas drilling, it's a little bit like less intensive on the material. There's also a limited use of them to certain materials. I mentioned it's not really applicable for all materials because some materials, like as I mentioned, acrylic, it's not really great for self-tapping screws. It's also not as strong as a bolt because the way that the threads have to be created to sort of self-tap them into the material is just not going to be as strong as a bolt because the threads are already cut into the bolt. So the process that you describe in your exam would be aligning the screw with the material surface and applying pressure whilst rotating the screw with a screwdriver or drill. And then you just screw the threads into the material as it advances. And then you just continue to screw until it is fully seated. And then you can check if it is securely fastened. Machine screws, on the other hand, are screws that have uniform threads that are designed to be tapped into holes or nuts. Be fastened into tapped holes or nuts. So basically something that's already got a thread on it. The uses of this would be for like electronic assembly, but also just machinery parts in general. And the pros of it is that it creates a very strong fastening and it's reusable and creates a precise fit, which means, and when I mean reusable, it means not only can we reuse the fastener, but we can also disassemble the part. Cons of it, however, is that it does require a tapped hole or nut, which can increase cost, and it has slower assembly than a self-tapping screw because you have to pre-drill and thread that hole. There's also a risk of the thread stripping, which could potentially mean the fastening would be redundant. The process we'd use in the exam would be to align the screw with a tapped hole or nut, and then simply turn the screw clockwise with a screwdriver or wrench or drill with a screwdriver bit on it, and then you'd engage the threads and tighten securely and then you'd avoid over tightening it to make sure that you don't damage the screw in any way. At which point you can then inspect the joint for tightness. Nuts and bolts. So nuts and bolts can be described as a fastening system where a bolt is inserted through a material and secured on the other side with a matching nut. So the uses of this would be particularly like construction or machinery assembly, but really anything. So sort of car parts. There's a very diverse application for nuts and bolts. Pros of it is that it is a strong joint that is easily removable and is versatile in many applications, but also that you don't have to create those threads within the hole because you're only relying on the bolt on the other side, which has the threads in it. So it's cheaper in that sense. The cons of it, though, is that it requires access to both sides. In some scenarios, you won't have access to both sides of the material, particularly if it's inside of a cavity. And it requires, it can loosen over time, which is an issue with it because obviously if there's any vibrations to the material, that can come undone. And that's why nuts and bolts aren't really used in aircraft because, as I mentioned earlier, rivets make more sense for that because you don't want the bolts to be coming undone mid-flight with all those vibrations and movements. There is also a corrosion risk without treatment. So the metals used for nuts and bolts can be corroding, and that can damage the integrity and strength of the joint. So the process you describe in your exam would be inserting a bolt through an aligned hole and then threading the nut onto the bolt end and tighten securely by hand initially, and then using a wrench or spanner to secure firmly. You'd then apply a washer if needed. You'd probably do that. You'd do that beforehand. You wouldn't apply the washer afterwards, which would disperse the pressure. That's what a washer does, by the way. It disperses the pressure of the fixture, which creates less damage to the material. And then once you've done that, you can check the fixture for tightness. Finally, we're going to look at metal wasting processes, and then I think I'm going to have a quick break before we do the wood processes. So the first metal wasting process is milling, which can best be described as a machining process that removes material from a workpiece using a rotary cutter to create shapes, slots, or holes. So the uses of this could be for engine parts or any sort of custom component, really. It's good for prototype manufacture and one-off production, or batch production as well. The pros of it is that it is high precision and creates versatile shapes. You can create any shape that you want. You don't have to rely on any molding. And that it leaves a fairly good surface finish, so not a rough surface finish. Cons of it, though, is of course we are wasting a lot of material that we are cutting off, and it requires a very skilled operator, which is costly. And not only that is it costly for a skilled operator, but it can also take them a lot of time because it is a time-consuming process. The process you describe in your exam is securing the workpiece to the milling machine table and then selecting the mount and appropriate cutter. I mean, like cutting bit. And then you'd set the machine and speed feed rate before positioning the cutter at the start point and engaging the cutter by lowering it onto the material, or moving the material along actually on this using the work table and using a cross traverse hand wheel. That's what it's called in the diagram. Along the cutter, or if it's computer controlled, along the programmed path. Next, we have turning, which in this case, we're talking about turning for metal. And it's described as a machining process where a cutting tool removes material from a rotating piece of metal work piece to create cylindrical shapes. So we are creating cylindrical shapes in this scenario. So this is typically used for like a shaft or a bolt, where we're creating something like which we need threads. So the pros of this is that it is very accurate for cylindrical parts, and that creates something with a nice surface finish, which is the finished part. It's also very efficient for round shapes, because we're creating something with a round surface profile. We're having something that's rotating. But the cons of it is that it does have it's limited to rotational symmetry. So basically something that has to be symmetrical when rotated. We can't use something that has a irregular profile. It does also require skill and a skilled operator, which again increases cost. And the tool can wear out over time, which will be our tool post, our cutting point, does wear out over time as the friction wears down on the material. The process you describe in your exam would be mounting the metal workpiece into the lathe chuck, which is the name for the sort of clamp in the lathe, and setting the cutting tool to the position and speed required. And then once you've done that, you can then start the rotation of the workpiece, and then feed the cutting tool into the workpiece gradually to shape the workpiece into the desired dimensions. And then once you've done that, you can perform any finishing processes if needed. Next, we're going to look at flame cutting, which is a process that uses a high temperature oxy-fuel flame, which just refers to burning oxygen, so like a blowtorch, to cut through metal by melting it and blowing away material. So the uses for this would be for like cutting a big steel plate, potentially demolition work. So if we're having to remove parts of a construction, The pros of it is that it cuts through very thick materials with portable equipment that is fairly low cost. The cons of it is that it is only effective on ferrous metals, and it does leave rough edges on materials, which means it's, as I mentioned, it's more applicable for demolition work and rough steel plate cutting. Because obviously, when you burn something, you're going to create slag on the material, which is a metallic waste product. But also, it could just the cutting will not be completely even on the edge. And there's also a zone around where the cut was made, which will be affected by that heat, and that can affect the strength of the material and long-term durability of that material. So the process you describe in your exam would be setting up the oxyacetylene torch and preheating the metal to the ignition temperature, at which point you can then activate the oxygen jet to cut through the material and move the torch steadily along the cut line as the material cuts. And then once you've completed the cut, you would turn off the torch and clean any cuts if necessary. Next, we've got plasma cutting, is incorrectly labeled as flame cutting. Plasma cutting is essentially using a high velocity jet of ionized gas, which is a conductive gas, to cut through electronically conductive materials. That's key, electronically conductive. So the uses of this would be in, for example, like sheet metal fabrication, but also in automotive repairs. Pros of it is that it is very fast, cuts through various different metals, just anything conductive. So obviously only metals, but most metals are conductive to an extent. Obviously, the conductivity of metals varies. And it also leaves a very clean edge on the material. It does require a power source, and it does also require very expensive equipment and the gas sources. It also is limited in thickness. So if you use a thicker piece of material with a plasma cutter, that will remove the whole clean edges element thing I mentioned. It will probably lead to rough edges just due to how the plasma arc will form. So the process you describe in your exam is essentially just connecting the plasma cutter to a power source and gas supply and setting the parameters such as the current and gas flow before positioning the torch over the metal surface and initiating the plasma arc, which is basically the electrical charge from the electrode in the torch electrode inside the plasma gun, creating an arc to the positively charged workpiece. At which point we then move the torch along the desired cut path and complete the cut and turn off the plasma arc. And then we can then clean up and inspect the cut edges. You are also expected to know laser cutting for metals, but because I already mentioned it earlier, I thought there's no point in repeating myself. Next, we're going to look at punching and stamping. So punching and stamping is a process that uses a punch and die to shear a metal or shape material, often used to create holes or surface features. So the uses of this would be for like metal enclosures or creating something like a washer. So the pros is that it is a very fast process that creates consistent results and it is good for a high volume. Cons, however, is that it is very expensive to create that die, so that contributes to tooling cost, and also is limited to thinner materials because we're not heating it in any way, we're just pressing it down. And it also creates waste through any sort of materials that we need to remove, any excess. So the process you'd need to describe is position the material on the die and align the punch above the desired area. Apply force via press or hammer, and the punch will shear the material into the die cavity, at which point we can then remove the punched scrap, remove the punched piece or scrap. And I'm going to leave it there for now, with wood processes being in the next one. So thank you all for watching, and I'll see you all next time.